pink color. So I'm pushing all of the charges up, which is going to force them to flow this way in the circuit.
Cool. Thank you.
Mm-hmm.
So once the piece of metal stops moving, like when it's stopped, it creates no charge, right?
Right. Everything goes to zero. So when the velocity is zero, the magnetic force is zero, the electric field is zero, the current is zero, the voltage is zero, nothing happens. You have to have that motion to be able to maintain those. Okay, now, does the idea make sense? Yeah? All right. So we have an example in the notes. Example 1, we want to compute the motional EMF and the current in the circuit for the following. So we have a conductor that has a length of 0.1 meter. This guy has a velocity of 0.1 meter per second. We're going to ultimately connect this to a resistor of 0.01 ohms. Our magnetic field is going to be 1 Tesla. All right, so the EMF, and I'm going to use this kind of script E for EMF, is equal to VBL, so 0.1 meter per second, 1 Tesla, and it's 0.1 meter long, is going to give me a voltage of 0.01 volts. Now, if I take this guy and I connect it to a resistor, and we want to know our current in the circuit, it's just going to be Ohm's law. We had 0.01 volts. The current is what we're looking for, 0.01 ohms. And we would have 1 amp flowing through our circuit. Now this is the basic idea behind an electrical generator. Okay, we saw a motor previously. A motor is going to convert electrical energy to mechanical energy. A generator does the opposite. It converts mechanical energy to electrical. And the idea, I've kind of abused my wrist today. I'm not very happy. The idea of a generator, or the use of a generator, is it's what every modern city in the United States uses. So if you have a citywide power system of some sort, like Idaho Falls has Idaho Falls Power, they use generators. If you're trying to remain off the grid and you decide you want to use solar power or something like that, that's a little different. But if you have a community approach to power generation, they use generators for this. Okay. So let's not worry about that force and work, but let's go up to example 2, where we have that rotating square loop again. Okay, now that generator that we just kind of talked about is great in terms of describing the theory behind this, but not so much in practice. For any system that you want to build, you want to make sure it's compact, at the same time giving you the maximum amount of energy necessary. So we really don't want to build a system where we have to slide a conductor some great distance L and then bring it back. And it just take up too much space. The other problem with that is when it's moving at its maximum speed, that's great. But as it's slowing down or speeding up, maybe because it's getting ready to turn or it's just turned, back and forth, that's going to send your voltage to zero. And if you have a community of 50,000 people that are depending upon that, you're going to get some cranky customers. So what we really need to do is figure out a system that is in constant motion, but doesn't ever change its position. And that's what rotation is going to allow us to do. So this guy is my square loop again. Like I said, I forgot that wood square loop at University Place, so I tried to create this one instead. So I'm going to have two edges of interest. The one that we're going to pay the most attention to is this side, and I folded up the edges of the paper so that we can distinguish, this is always the side that I'm going to look at. Okay, so in sticking with the picture that's in the notes, we're going to have a magnetic field. It's an external field that's always going to point straight up. Its direction doesn't change, and its value doesn't change. That's a nice constant field. And we have this guy on an axis, and we're going to allow it to rotate. So I'm going to look at a little charge right here on this edge, about where my finger is, right here in the middle. And as I rotate this guy, he's going to have a rotational velocity as it goes around the loop. And we're going to figure out the direction of the forces that are acting on him. So this is going to be our right-hand rule again, QVB. So here's my Q. V is up. B is up. Force is 0, right? Because I can't take that cross product. So right here in this orientation, nothing happens to this charge. But as I rotate it to here, now I'm going to have Q is moving to my left. My right hand's not going to like this. My field is up. This charge is going to feel a force that's going to push it out towards you guys. And we could do the same thing down here. This charge is going to be moving to my right. If we apply right-hand rule to that guy, this charge would be pushed back to me. So we've just created a current that's going to go around the loop this way. So my folded edge is coming out towards you. Okay, everybody see that part? Yeah? Okay, when I get back to this point, everything goes to 0 because V and B are parallel. And now we get to this point. If we apply the right-hand rule again, what we would see is this same charge down here that we're kind of tracking is now moving to my right. Right-hand rule is going to send it back towards me, and we're going to create a current that flows this direction. So this part, this edge that was originally traveling towards you is now traveling towards me. And then we go to 0. And then we get current towards you, 0, current towards me, 0, and so on. As long as we maintain that rotation. So what this would look like, if we plotted it, is 0 current to a maximum, back to 0, to a maximum the other way, through 0, and so on. Okay, alternating current. Now the time between these peaks is going to depend upon how quickly that rate of rotation is. The faster this thing rotates, the higher this frequency is. And they're both defined by omega. Most generators, most community, citywide generators operate at about 60 hertz, which makes omega about 377 radians per second. Now here, if you're on Idaho Falls Power, not Idaho Power or Utah Power or Rocky Mountain Power, or I don't even know what all of the companies are around here, but if you are part of Idaho Falls Power, they have, I believe, 5 turbines throughout the city. There's one just right close to Broadway. It's about underneath the water tower, if you guys know where the old water tower is. And what the city does is they use the water pressure from the river. So they actually divert part of the river, and they use water pressure to rotate the turbine. As that turbine rotates inside a magnetic field, it produces the power that we use. So I think I've mentioned a couple of times that Idaho Falls Power is inexpensive compared to a lot of others. This is why. That input energy that they need to make that mechanical rotation is cheap. Other types of energy that you could use for that rotation: fossil fuels, nuclear energy, wind, just about everything except solar. It just needs to be some sort of mechanical energy input. But if you live in a community that uses fossil fuels, they still use generators. Nuclear energy, they still use generators. It's just how you make the turbine rotate to begin with. Now here's something that I think is kind of funny. I don't know if any of you guys are from California originally. I'm going to pick on California just a little bit. They have some laws on the books that say they have to use a certain percentage of renewable energy. So hydroelectric, which is what we use, geothermal, solar, wind, no fossil fuels, no nuclear. I don't know if the city still does this, but we used to sell the power that Idaho Falls produces to California because it's clean energy and it matches, what the laws on the books. And then we don't care, so we would buy cheaper power someplace else, and the city could turn a profit by selling power. The thing that I find most ironic about this is once it's put out on the city power grid, or actually it's not even city power grid, there's like 3 power grids in the country. You have the Western, you have the Eastern, and then there's kind of this third one in Texas. Once it's put on that Western grid, it all looks the same. So California is tapping into the exact same energy that we are. They're just paying more for it because they have to have a certain percentage of renewable energy, even though it's not possible to go, to tap energy from that grid and say, I just want the renewable stuff. It's just all voltage at that point. I think that's kind of funny myself, but. All right. Now, does that idea make sense? We're going to come up with an equation here in a sec, as long as the...
Can you explain how this is different from the loop that we've already looked at? Is there still a current in this loop and we're just interested in that one charge, or is there...
There is still a current. So the previous time that we looked at this loop, what we did is we had our magnetic field, we ran current through it, and that produced a torque that made it rotate. So the current was the electrical energy, and then from that we got mechanical energy out of it. Current made it rotate. This guy is reverse. The rotation is making the current. So we're putting mechanical energy in instead of electrical energy in.
And where's the...
This would have been so... Oh, sorry. I was going to say this would have been so helpful for the lab.
Yeah, it is the stuff that you're doing in the lab right now. For some of you, you're doing it tonight. Where'd my little menu thing go again?
Dave said it was the only lab that made me cry.
I didn't quite hear that. It's the only lab what?
Dave said it was the only lab that made me cry.
When he took it or just teaching it?
When he took it.
Probably both from all of our questions.
Yeah.
Yeah, I think the RLC one's worse myself, but... All right, there's another question.
So where does the magnetic field come from in this generator?
It's an external field, so you would probably have to have a secondary system that had like an electromagnet that would surround the turbine. So imagine a coil of wire that surrounds it that has like an independent power source. It doesn't come from within the generator. It's something you also have to supply. And another way of doing this is having that, we're rotating the square loop, but that can stay stationary and you can move the magnet around it. You get the same effect. But you wouldn't want to use just like chunks of iron or anything like that, because you need to be able to have a stable, constant strength and constant direction field. So that means an electromagnet. Let's see. Okay. Any other questions? Nope. All right. Okay, I don't remember what I'm sharing here. I'm sharing my tablet. Okay. Okay, so we found that this EMF earlier was equal to the speed times the B field times the length of the conductor. We're going to adapt this to our rotating loop. Some of this is going to go back to first semester physics. For some reason, this is an equation that people just seem to hate. They don't like to remember this guy. But V is equal to R omega. So V is your translational velocity, omega is the rotational velocity, and they're related to each other by R. Is this seeming slightly familiar? Kind of, sort of. All right.
R is the radius, right?
Yes.
Okay.
So if I go back to that picture that's in example 2, I've defined that radius as B over 2, little b over 2. So in place of this guy, I'm going to put in R omega, and R is B over 2. And then also in that other picture, that rotating square loop, the length of the conductor, the length of this side, I called that A. Okay, next thing. This guy isn't always going to supply a nice constant voltage. It depends upon where it is in its rotation. So right now, I'm going to say my angle is 0. We're going to increase it to 90. And as I increase it, I increase my voltage. And then we're going to decrease the voltage. We're going to go to 180. Okay. Somehow I need to take into account that angle, and that angle is going to depend upon the time that I look at it. So this is where the sine omega t comes from. Omega t is equal to our angle. Oops, too big. One last thing, and then we're just going to simplify the whole thing. What I've just written is going to be the voltage that this side is going to produce. but this side is also going to produce it as well, this edge and this edge. So I actually have two of these. Okay, so my little a times the little b is going to be the area of my loop. So my 2's will cancel. My little a and my little b are the area. And then I will have the rotation rate, the magnetic field, sine omega t. Usually it's written omega AB. Reorder the variables just a little bit. Okay, that's for one loop. If I wrap the wire of my conducting coil multiple times, then I throw an N out front of that, and that will affect the amount of voltage that we can get out of that.
Is this an equation we would have that you give us, or would we have to figure it out at the time?
I've done both in the past. I've had people kind of derive this, and then I've just given them examples. I'm thinking since I want to make this next test a little bit easier, I'm going to go ahead and give it to you. Okay, so that gets us through several pages, actually, of the notes. Okay, so the next point where I'm looking at in the notes is where it's titled the alternator. Let's see, 1, 2, 3, no, 2. 2 pages after that square loop. This is the basic idea behind an alternator also. So you have a conducting coil, you rotate it in a magnetic field, and it will produce an alternating voltage. Hook that up to a circuit, and then you will have an alternating current as well. Now, one problem that we run into, though, alternating current cannot be used to recharge a battery. We use rechargeable batteries a lot. We've got rechargeable batteries in cell phones and tablets, your computer, your car. My robot vacuum has a rechargeable battery. My remotes do. I'm trying to look around and see what rechargeable things that I have. So when you have a battery, it's using a chemical reaction to produce that voltage. Once that chemical reaction has been depleted, you need to run current back through it the opposite direction to recharge the battery. If I supply a current that's actually going forwards and then backwards and then forwards and then backwards because it's changing direction, I'm never going to be able to recharge this. I need to supply it with a nice direct current. Most of your devices will come with some sort of little block that's attached to the power cord or that you plug the power cord into. This guy, this is the thing that will convert alternating current into direct. So this plugs into the wall outlet. The outlet is supplying alternating power. This converts it into direct. So then when I plug, the cord in here, this is what gets supplied to, let's see, this is for one of my tablets. Okay. Your cell phones, computers, tablets, all of these things are going to have some sort of block on them, and that's what this guy does, is it converts AC into DC. The other way of doing it, let's see, let me share the notes again real quick. Stop share and share notes. Okay, so like we said, an alternator is going to supply an alternating voltage. Can't really be used to charge a battery. So you can put a gap in it. So every time it gets to, okay, this is where we get maximum voltage. Let's say when it gets to this point, we actually cut the connection so that there's no current flowing through here at all. And we just let inertia carry it through. So what you would get is a voltage that looks more like this picture here. You don't get any negative values. That can be used to charge a battery. There are also little semiconductor devices that are called diodes, and diodes will only allow current to flow one direction. So let's say your current needs to flow to my left. Alternating current would go this way. The diode would block it, so it can't go backwards, and then it would go forwards again. So you would only get forward current. And we call that rectifying. So anytime that we try and convert, say you have a positive and a negative current, and you take the negative and you make it positive, or you just eliminate this guy, we call that rectifying. Okay, now those ideas make sense. Yeah? Okay. All right. As it turns out, though, when we just conjured up our equation for our rotating square loop, all we looked at was the motion. Technically, I could get the same effect if I also changed the field. So instead of looking at this guy as it's moving, let's look at the amount of area that the field lines could pass through. So if I have these magnetic field lines that are pointing straight up, I can get more field lines through this way, and then they go to 0. So the area that the field lines can penetrate into changes as I rotate this. Any change in area can create a magnetic field if you have, a voltage if you have the magnetic field. So I honestly don't know how we could build something like this, but let's say I just have a conducting coil without changing its speed or anything like that. If I could just make it shrink and grow and shrink and grow, that could create a voltage. Or if I have this conducting coil and I expose it to a magnetic field that changes in time, that can create a voltage. So Faraday's law looks at all of those cases. We're looking at both area and the magnetic field as it can change in time. So it's a bit more inclusive than the way we just did it. So let's define our flux. Very similar to our electric flux. If you remember, I know how much you guys liked Gauss's law, but we defined flux earlier as E dot A with our E fields and our areas. Now we're going to have a magnetic flux as well. It's a measure of the amount of field lines that can pass through an area. And this is that same area vector that we had to create, right? It's perpendicular to the surface area. Its magnitude is whatever the area of the loop is. Okay, if I can change this flux in time, I will create a voltage. So any change, oops, sorry, we don't do derivatives, I forgot. So any change in either one of these guys will give me a voltage. Somebody somewhere decided there should be a negative out front, so there's a negative out front. It's just there for convention. So that means that I could have a changing field times an area, or I can also have a changing area times my field. Oh, and the negative thrown out front. This is Faraday's law. Okay, if we have multiple loops, then we would just throw an n out front for the number of loops that you've got. All right, so next in the notes, there's a transformer. We're going to come back to those. We'll talk about them in more detail. We're also going to talk about current wars and a little bit of history, but let's jump to example 3. Okay, so in this example, we have a solenoid, bunch of loops of wire. It tells us that this guy has 500 turns or 500 loops. It has a radius of 4 centimeters. I want that in meters. It tells me that my magnetic field is changing in time. So that guy is going to be 0.2 Tesla per second. And we want the EMF from that. So if I go back up here to this specific version of Faraday's law, the area is not changing in this particular example. So that means this delta A is 0. That whole term is going to be 0. Not always the case, but it is the case for this problem. So that means Faraday's law is now going to reduce down to our changing field times the area times the number of loops. So I have 500 loops. My changing field is 0.2 Tesla per second. And my area is going to be pi r squared. Now, if I multiply all of that out,
You have a negative in there.
yeah, we're going to talk about him in a sec. So a couple things about that negative. It really is just there for convention, and a negative voltage doesn't really mean a whole lot. I mean, turn your voltmeter around, plug it up, connect the leads opposite, and you'll get a positive voltage. So a lot of times that negative just kind of disappears. If you don't like disappearing negatives because you can't mathematically explain it, you can go ahead and keep it on there. The other thing, in this particular problem, I didn't really define how the magnetic field was changing, if it was getting larger or smaller. That could have an effect on the direction as well. I'm not going to mark you wrong if you don't have that negative thrown in. Now, in the second part of this problem, it tells us that instead of the magnetic field being nice and straight down through the center of that solenoid, we're now going to send it in at an angle of 30 degrees. So when I have a dot product like this guy up here, that means that my vectors need to be parallel to each other. So that B field in that area, I need to force them to be parallel. The way I do that, let's see if this is my area. And this is the B field. That B field can be broken up into components. I need that BX component. It's adjacent to my angle, so that's going to be AB cosine of that angle. So if I change that B field from nice and parallel to an angle of 30 degrees, what I really need to do is take this answer of 0.5 volts and multiply it by the cosine of 30, which is like 0.4, 30 cosine, 0.44. Negative if you want it. Okay, so that doesn't quite get us to where I wanted to for tonight, but I think that's still going to leave us in an okay spot. So quiz really quick. Things that could potentially show up. Let me write these down, then you guys kind of pick and choose. We could have a velocity selector. We could do magnetic fields of Earth or Sun. We could do a motor. I'm not loving that one because it's been a while. I mean, we've had like 3 weeks since we've done that, and I'm not sure that I've given you enough warning. We could do a generator. If I did a velocity selector, it would probably include a mass spec as well. Probably not going to ask you anything about ferro, para, or diamagnetic materials. So of these four, what do you guys think you're most prepared for?
I would say either the velocity selector or the magnetism of the Earth and Sun.
These two?
I'd say generator.
Generator
has the most math.
Would the generator be just like plugging into that equation basically?
It would probably be like the very first one that we did. So figure out the voltage, and then from there figure out current, something like that.
I would be cool with that one.
Honestly, what is the motor again? Is that, like, what is that?
That was the, before the break. You remember that wood square loop that I had in class?
Okay, so that was the first loop.
Yeah, it was the first loop. Basically what you do is you apply right-hand rule. You you choose a current in a particular direction. I think we chose counterclockwise just to start. You have a magnetic field in a particular direction. You figure out the forces and the torques and look at what direction the thing's going to rotate. And then the example that we would use is like a power drill. It's going to make something mechanically rotate. Power tools use motors all the time. I'm going to say motor is probably not the one you want on the quiz. Okay. Do you want all three of those? That's an awful long quiz.
No.
I mean, it's online. I can make it give you more time, but...
Yeah, I mean, I feel like it'd be nice to get exposed to all of those problems before the exam, so I'm not that used to that. I don't know if anybody else feels the same way.
Okay. All right, so let's do a couple of questions, probably one from a velocity selector, one from a mass spec, a couple that would deal with the magnetic field of the Earth or the Sun, probably not both. Do you have a preference whether it's Earth or Sun?
I like the sun.
Earth.
I really need you to agree. All right. One of them. I'm not going to make you do both. And then maybe a question or two from generators. It'll be multiple choice. But keep in mind, when it comes to your test, you know, all of this stuff is still fair game for your test. It's not multiple choice. Like these two would probably be short answer. So try not to get too caught up on the idea of getting used to an online multiple choice test. So, okay, I will try and get this posted tonight. If not, it'll be tomorrow. Due Monday morning by 6 a.m. And those of you that have not done it, please go in and take that sample test where I need you to upload something to me. All I'm looking for is that you can send me a file. So it can be a picture, a meme. I can change the background so I can teach from some other location if there's something you want to see instead of the stuff that's hanging on my walls, then send me that picture. Okay? All right. Questions about anything? Nope. All right. Good luck in lab tonight. How'd it go Tuesday? Okay.
Not bad. We had another Zoom meeting at 1 on Wednesday to kind of ask more questions because we were confused about whether it's about the flux or like the direction of magnetic field lines that determines, I think, what direction the current's going to go to oppose that. You know what I mean? I think we got confused. But Dave said he was going to